All right, so this first problem on part 2 of the test has to do with permutations. So you're given two permutations in cycle notation, and I suppose it's okay to draw it pictorially. Well, the 1, 2, 3, 4, 5 looks like this. If you were going to draw this with pictorial diagrams, 3, 4, 5, the first part would look like this, and the second part would look like 6, 7, 8. Oh, 6, 7, 8, like that. Okay. So that's how it would look, and let's erase that. Okay. So, but let's go ahead and write in Tableau notation. In Tableau notation, you basically look at each element and see what it goes to. So the elements are 1, 2, 3, 4, 5, 6, 7, and 8. Now, if you look at this picture, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1, 6 goes to 7, 7 goes to 8, 8 goes to 6. All right, so that's for part A, and that's kind of a warm-up problem. Now, for most of this, you actually use the cycle notation because it's more insightful. So, for instance, for part B, the order of the order is equal to the LCM of the cycle lengths. The cycle lengths are 5 times 3. There's no GCD, so it's just equal to 15. So that's the answer for part B. Now for part C, we've seen how to express cycles using transpositions. So mu, there's a couple ways to do it. You can say mu equals a 1, 5, 1, 4, 1, 3, 1, 2. That's one way. And then sigma is equal to, you can write sigma is equal to 6, 8, 6, 7. So you could write them as the product of all these transpositions. So mu sigma is equal to 1, 5, 1, 4, 1, 3, 1, 2, sorry, 1, 2. Let's adjust 1, 2. 1, 2. And then you can also do 6, 8, 6, 7. That's fine. Okay. In fact, you could put the sigma on the other side because the sigma and the mu commute because they're disjoint cycles. And where's my mouse? You could write it other ways. This is a perfectly acceptable answer, but there's another way that people have written cycles, which is you can do 1, 2, 2, 3, 3, 4, 4, 5, and then times 6, 7, 7, 8. That's another way. That also works. All right. So that either one, and there are other options as well. So let's go to part D. So this was part C. And then part D is, well, remember that even permutation is the same thing as this if and only if the permutation is the product of an even number of cycles. Okay, that's a result we proved in the chapter. So now in this case, I'm sorry, not cycles, even number of transpositions, sorry. They don't have to be disjoint transpositions. They can be any kind of transpositions. Okay. All right, so how many transpositions do we have? 1, 2, 3, 4, 5, 6. So mu sigma is the product of 6 transpositions. So that means that mu sigma is even. Okay, and that's really the proof. because the definition of even permutation means can be written as the product of an even number of transpositions. Right? So that's what we got. And I think that's the end of this problem. Okay, since that was short, let's go on to question 2. Okay, so let's express mu sigma inverse in cycle notation. All right, now I had mu sigma as a product of transpositions. You can simply express the, so let's just repeat that. Mu sigma, what did we have here? We had, well, I said, for instance, I had 1, 5, 1, 4, 1, 3, 1, 2, and then times 6, 8, 6, 7. Okay. Now mu sigma inverse is equal to the transpositions written in reverse order. Okay, written in reverse order, so that's equal to 6, 7, 6, 8, and then 1, 2, 1, 3. There are other ways to do this. 1, 4, 1, 5. Now I can just go ahead and work out the cycle notation for this. In this case, 1 goes to 5, and that's the only 5 that appears, so that means that 1 goes to 5. Then 5 goes to 1, 1 goes to 4, so 5 goes to 4. And then 4 goes to 1, 1 goes to 3, so 4, 3. So this is the familiar inverse cycle. Well, once you get 2, 2 goes to 1, so it closes off. Then here you have 6. 6 goes to, whoops, I did this backwards, sorry. No, 6 goes to 8, yeah. And then 8, if you look at 8, 8 goes to 7, so you get this. All right, so that's the inverse. Now, for part B, it would have been good if you recognized the relationship between part B and part A. So this is part A. Part B says I want mu sigma theta is equal to 2468. Now what that means is that if I multiply both sides by mu sigma inverse, that's equal to mu sigma inverse times 2468. Now, I think that this illustrates an important and general technique that you see not just in abstract algebra, but linear algebra, and even in basic algebra in high school. You want to solve an equation, you need to get your unknown by itself on one side, and to do that, you use inverses. Right? So mu sigma inverse times mu sigma, that's just equal to ID. And ID times theta is equal to theta. Okay. So that gives me theta simply as mu sigma inverse times 2468. Now, fortunately, I have mu sigma inverse from the previous problem, so that's equal to 1, 5, 4, 3, 2 times 687 times 2468. Okay. All right, so let's work it out. That's equal to, let's see what 1 goes to. Well, 1 goes to 5, 5 goes to 4. Now 4 goes to 6, which goes to 8. So we have this. Then I have 8 goes to 2, which goes to 1. So that closes this guy off. And then now let's see what 2 goes to. 2 goes to 4, which goes to 3. Then 3 goes to 2, so that's there. And then let's see, what else do we have? We have 1, 2, 3, 4, 5. Let's see what 6 and 8 go to. 6 and 7 go to. 6 goes to 8, which goes to 7. And let's see if 7 goes to 6. 7 actually goes to 6. So this is what theta is. So you have to do all of the cycles and do the calculation. All right, so I think that's all there was for this part. Oh no, 6C. All right, now see, there was actually a mistake. It turns out that it's not possible to do this with a single transposition. I should have said a cycle of length 8. Now some people did some stuff which was good, and instead of using a transposition, they used something else, which was great. So I gave full credit for that. So here it says, find a transposition tau such that tau mu sigma is a cycle of length 7. Express the product tau mu sigma in cycle notation. It may help to draw a wheel picture of mu and sigma. So let's go ahead and draw a wheel picture of mu and sigma. So here I have mu and sigma. Oops, sorry, wrong color. Let's give myself a little bit more room. So mu was 1, 2, 3, 4, 5. And here's my wheel. And then here I have 6, 7, 8. Now somehow we want to join these two cycles together using a transposition. So suppose we consider putting in this transposition here, 2, 6. Okay, sorry, I should make that in green. So somehow we want to consider joining these two cycles together. So we're going to have some kind of transposition that goes across and joins the cycles. So let's consider adding the transposition 2, 6, which would go like this. And let's think about what happens when we do that. Now we're putting 2, 6 on, we're putting the transposition on the left, so it follows the arrows that we have here. So what that means is that if I add 2, 6, so let me just write down here what the result will be. So here I'm going to say add 2, 6. Okay. So the result of 2, 6 times mu sigma. If you look at the cycle picture, so let's draw this again. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then this is 6, 7, 8. Okay. Now, because these arrows are followed after the other arrows, what's going to happen is that 1, instead of ending up at 2, is going to go straight to 6. So this 1 will end up going to 6. And this 8, instead of going to 6, will end up going to 2. So 8 will go to 2. But everything else is the same. All right, so what you get is a cycle like this. And this is a cycle with 8, which I counted wrong when I made up the test. So if you gave this something like this, if you gave 2, 6 times mu sigma is equal to 1, 6, 7, 8, 2, 3, 4, 5. And it's a cycle of length 8. Now, if I want a cycle of length 7, I'm going to have to do something else. I'm going to have to take out one of these guys so that it doesn't move. So, for instance, if I added in front of this a 2, 3, if I put 2, 3 in front, sorry, this is a sigma and this is a 6, and it's not really clear that there's a difference there. This is a 6 and that's a sigma. Let me try to make it different. Okay. All right, now if I put the 2, 3 in front, what would happen? Well, I draw that same cycle, but 2, 3 would mean that instead of 8 going to the 2, we go directly to the 3. And 2, instead of going to the 3, would stay to the 2. So this would turn out to be, would basically take the 2 out of the cycle and give you 1, 6, 7, 8, 3, 4, 5. And that's a cycle of length 7. Okay. Let me draw that so you can see it. If you took 2, 3, so let's say what we have here. Here you have 1, 6, 7, 8, 2, 3, 4, 5. So this is the original cycle. And then suppose we put 2, 3 in there. And let me see if I can do it so that you can see what's happening. So if I put 2, 3 in there as an additional cycle, okay, so I added 2, 3. What's happening here? And as I said, you follow the arrows, then 8 goes directly to 3, and 2, because you follow the arrow, 2 originally goes to 3, but you follow the arrow back to 2, and so 2 goes to 2. Okay. So you do have a cycle of length 7. Now, this is not a transposition, but it is a 3 cycle. So let me trying to find my mouse. Okay, so that means, so that tells me that if I combine these two together, where's my mouse? Okay, if I combine these two together, that's going to give me 2 goes to 6, and 6 goes to 3. So that means 2, 6, 3 times mu sigma is equal to 1, 6, 7, 8, 3, 4, 5, which is a cycle of length 7. Okay? So that's how you could do that. All right, let me stop there and do the last one separately.